Welcome. This video will cover the Operational Excellence Pillar. The Operational Excellence Pillar focuses on the ability to run and monitor systems to deliver business value and to continually improve operations. Key topics include managing and automating changes, responding to events, and defining standards to successfully manage daily operations. There are 6 design principles for operational excellence in the cloud. First, you have perform operations as code. This is where you define your entire workload, that is, applications and infrastructure, as code. By performing operations as code, you limit human error and enable consistent responses to events. Next, we have annotate documentation. Here you focus on automating the creation of annotated documentation after every build. Annotations can be used as input to your operations as code. Next, we have make frequent, small, reversible changes. You should design workloads to enable components to be updated regularly. Make changes in small increments that can be reversed if they fail. Next, you have refine operations procedures frequently. Here you look for opportunities to improve operations procedures and update them as they evolve. Next is anticipate failure. This is where you identify potential sources of failure so that they can be removed or mitigated. Test failure scenarios and validate your understanding of their impact regularly. Finally, we have learn from all operational events and failures. This is where you share what is learned across teams and throughout the entire organization. The foundational questions for operational excellence fall under 3 best practice areas: prepare, operate, and evolve. Operations teams create and use procedures to respond to operational events and validate the effectiveness of these procedures to support business needs. Operations teams collect metrics that are used to measure the achievement of desired business outcomes. Business priorities and customer needs change over time. It's important to design operations that evolve in response to change and to incorporate lessons learned through their performance. For prescriptive guidance on implementation, see the Operational Excellence Pillar White Paper. Thanks for watching. See you in the next video. Welcome. This video will cover the security pillar. The security pillar focuses on the ability to protect information, systems, and assets while delivering business value through risk assessment and mitigation strategies. The security pillar focuses on the key areas of protecting confidentiality and integrity of data, identifying and managing who can do what, or privilege management, protecting systems, and establishing controls to detect security events. There are 7 design principles that can improve security. First up, implement a strong identity foundation. Here you implement the principle of least privilege and enforce separation of duties with appropriate authorization for each interaction with your AWS resources. Next is enable traceability. This is where you monitor, alert, and audit actions and changes to your environment in real time. Integrate logs and metrics with systems to automatically respond and take action. Next is apply security at all layers. Here you apply defense in depth and apply security controls to all layers of your architecture. For example, edge network, virtual private cloud, subnet, and load balancer, and every instance, operating system, and application. Next up is automate security best practices. This is where you automate security mechanisms to improve your ability to securely scale more rapidly and cost effectively. Next is protect data in transit and at rest. Here you classify your data into sensitivity levels and use mechanisms such as encryption, tokenization, and access control where appropriate. Next, keep people away from data. This is where you reduce the risk of loss or modification of sensitive data due to human error. Create mechanisms and tools to reduce or eliminate the need for direct access or manual processing of data. Finally, prepare for security events. This is where you have an incident management process that aligns with organizational requirements. Run incident response simulations and use tools with automation to increase your speed of detection, investigation, and recovery. The foundational questions for security fall under 5 best practice areas known as identity and access management, detective controls, infrastructure protection, data protection, and incident response. Before you architect any system, you must put security practices in place. You must be able to control who can do what. In addition, you must be able to identify security incidents, protect your systems and services, and maintain the confidentiality and integrity of data through data protection. You should have a well-defined and practiced process for responding to security incidents. These tools and techniques are important because they support objectives such as preventing financial loss or complying with regulatory obligations. For additional information, see the Security Pillar White Paper. Thanks for watching. See you in the next video. Welcome. This video will cover the reliability pillar. The reliability pillar focuses on the ability of a system to recover from infrastructure or service disruptions, dynamically acquire computing resources to meet demand, and mitigate disruptions such as misconfigurations or transient network issues. The reliability pillar focuses on the following key topics: setup, cross-project requirements, recovery planning, and handling change. There are 5 design principles that can increase reliability. First, we have test recovery procedures. This is where you test how your systems fail and validate your recovery procedures. This practice can expose failure pathways that you can test and rectify before a real failure scenario. Next is automatically recover from failure. Here you monitor systems for key performance indicators and configure your systems to trigger an automated recovery when a threshold is breached. This practice enables automatic notification and failure tracking, and for automated recovery processes that work around or repair the failure. Next is scale horizontally to increase aggregate system availability. This is where you replace one large resource with multiple smaller resources and distribute requests across these smaller resources to reduce the impact of a single point of failure on the overall system. Next up, stop guessing capacity. Here you monitor demand and system usage and automate the addition or removal of resources to maintain the optimal level for satisfying demand. Finally, manage change in automation. This is where you use automation to make changes to infrastructure and manage changes through automation. The foundational questions for reliability fall under 3 best practice areas known as foundations, change management, and failure management. To achieve reliability, a system must have both a well-planned foundation and monitoring in place. It must have mechanisms for handling changes in demand or requirements. The system should be designed to detect failure and automatically heal itself. To learn more, see the Reliability White Paper. Thanks for watching. See you in the next video. Welcome. This video will cover the performance efficiency pillar. The performance efficiency pillar focuses on the ability to use IT and computing resources efficiently to meet system requirements and to maintain that efficiency as demands or technologies change. The key areas to review are selecting the right resource types and sizes based on workload requirements, monitoring performance, and making informed decisions to maintain efficiency as business needs evolve. There are 5 design principles that can improve performance efficiency. First up is democratize advanced technologies. Here you consume technologies as a service. For example, technologies such as NoSQL databases, media transcoding, and machine learning require expertise that is not evenly dispersed across the technical community. In the cloud, these technologies become services that teams can consume. Consuming technologies enables teams to focus on product development instead of resource provisioning and management. Next, we have Go Global in Minutes. This is where you deploy systems in multiple AWS regions to provide lower latency and a better customer experience at minimal costs. Next up, use serverless architectures. Here you utilize serverless architectures to remove the operational burden of running and maintaining servers to carry out traditional compute activities. Serverless architectures can also lower transactional costs because managed services operate at cloud scale. Next is experiment more often. This is where you perform comparative testing of different types of instances, storage, or configurations. Finally, have mechanical sympathy. Here, you use the technology approach that aligns best to what you are trying to achieve. For example, consider your data access patterns when you select approaches for databases or storage. The foundational questions for the performance efficiency pillar fall under 4 best practice areas, known as selection, review, monitoring, and trade-offs. You must use data to design and build a high-performance architecture. It's important to gather data on all aspects of the architecture, from the high-level design to the selection and configuration of resource types. You must review your choices periodically to ensure that you are taking advantage of new AWS services. Don't forget to perform monitoring so that you are aware of any deviance from expected performance and can take prompt action to remediate them. Finally, use trade-offs in your architecture to improve performance, such as using compression, using caching, or relaxing consistency requirements. To learn more, see the Performance Efficiency Pillar White Paper. Thanks for watching. See you in the next video. Welcome. This video will cover the cost optimization pillar. The cost optimization pillar focuses on the ability to run systems to deliver business value at the lowest price point. This pillar focuses on the areas of understanding and controlling when money is being spent, selecting the most appropriate and right number of resource types, analyzing spending over time, and scaling to meet business needs without overspending. There are 5 design principles that can optimize costs. First, we have adopt a consumption model. This is where you pay only for the computing resources that you require. Increase or decrease usage depending on business requirements, not by using elaborate forecasting. Next up, measure overall efficiency. Here, you measure the business output of the workload and the costs that are associated with delivering it. Use this measure to know the gains that you are making from increasing output and reducing costs. Next, stop spending money on data center operations. AWS does the heavy lifting of racking, stacking, and powering servers, which means that you can focus on your customers and business projects instead of the IT structure. Next is analyze and attribute expenditure. The cloud makes it easy to accurately identify system usage and costs and attribute IT costs to individual workload owners. Having this capability helps you measure return on investment and gives workload owners an opportunity to optimize their resources and reduce costs. Finally, use managed and application level services to reduce cost of ownership. Managed and application level services reduce the operational burden of maintaining servers for tasks such as sending email or managing databases. Because managed services operate at cloud scale, cloud service providers can offer a lower cost per transaction or service. The foundational questions for cost optimization fall under 4 best practice areas, known as expenditure awareness, cost-effective resources, matching supply and demand, and optimizing over time. Similar to the other pillars, there are trade-offs to consider when evaluating cost. For example, you may choose to prioritize for speed, going to market quickly, shipping new features, or simply meeting a deadline, instead of investing in upfront cost optimization. For another example, designing an application for a higher level of availability typically costs more. You should identify your true application needs and use empirical data to inform your architectural design decisions. Perform benchmarking to establish the most cost-optimal workload over time. To learn more, see the Cost Optimization Pillar White Paper. Thanks for watching. See you in the next video. Welcome. This video will cover reliability and availability. In the words of Werner Vogels, Amazon CTO, everything fails all the time. One of the best practices identified in the AWS well-architected framework is to plan for failure, which means application or workload downtime. You need to architect your applications and workloads to withstand failure. There are 2 important factors that cloud architects consider when designing architectures to withstand failure: reliability and availability. Reliability is a measure of your system's ability to provide functionality when desired by a user. Because everything fails all the time, you should think of reliability in statistical terms. Reliability is the probability that an entire system will function as intended for a specified period. Note that a system includes all system components, such as hardware, firmware, and software. Failure of system components impacts the availability of the system. To understand reliability, it is helpful to consider the familiar example of a car. The car is the system. Each of the car's components, for example, the cooling, ignition, brakes, must work together in order for the car to work properly. If you try to start the car and the ignition fails, you cannot drive anywhere. The car is not available. If the ignition fails repeatedly, your car is not considered reliable. A common way to measure reliability is to use statistical measurements such as mean time between failures, what's known as MTBF. MTBF is the total time in service over the number of failures. Let's say that you have an application that you bring online Monday at noon. The application is said to be available. It functions normally until it fails Friday at noon. Therefore, the time to failure, or the length of time the application is available, is 96 hours. You spend from Friday at noon until Monday at noon diagnosing why the application failed and repairing it, at which point you bring the application back online. Therefore, the time to repair is 72 hours, and you had no weekend. Then it happens again. The application fails on Friday at noon. You spend from Friday at noon until Monday at noon repairing it, and you bring it online Monday at noon. Let's say this failure, repair, restore cycle happens every week, and you don't get a weekend. You can now calculate the average of these numbers. In this example, your mean time to failure is 96 hours, and your mean time to repair is 72 hours. Your mean time between failures is 168 hours, or 1 week, which is the sum of the mean time to failure and the mean time to repair. As you just learned, failure of system components impacts the availability of the system. Formally, Availability is the percentage of time that a system is operating normally or correctly performing the operations of it, or normal operation time over total time. Availability is reduced anytime the application isn't operating normally, including both scheduled and unscheduled interruptions. Availability is also defined as the percentage of uptime, that is, length of time that a system is online between failures, over a period of time, which is commonly 1 year. A common shorthand when referring to availability is the number of nines. For example, 5 nines means 99.999% availability. A highly available system is one that can withstand some measure of degradation while still remaining available. In a highly available system, downtime is minimized as much as possible and minimal human intervention is required. A highly available system can be viewed as a set of system-wide shared resources that cooperate to guarantee essential services. High availability combines software with open standard hardware to minimize downtime by quickly restoring essential services when a system, component, or application fails. Services are restored rapidly, often in less than 1 minute. Availability requirements vary. The length of disruption that is acceptable depends on the type of application. Take a moment and study the common application availability design goals and the maximum length of disruption that can occur within a year while still meeting the goal. The table contains examples of the types of applications that are common at each availability tier. Though events that might disrupt an application's availability cannot always be predicted, you can build availability into your architecture design. There are 3 factors that determine the overall availability of your application. First, fault tolerance refers to the built-in redundancy of an application's components and the ability of the application to remain operational even if some of its components fail. Fault tolerance relies on specialized hardware to detect failure in a system component, such as a processor, memory board, power supply, I/O subsystem, or storage subsystem, and instantaneously switch to a redundant hardware component. The fault-tolerant model does not address software failures, which are the most common reason for downtime. Secondly, scalability is the ability of your application to accommodate increases in capacity needs, remain available, and perform within your required standards. It does not guarantee availability, but it contributes to your application's availability. And third, recoverability is the ability to restore service quickly and without lost data if a disaster makes your components unavailable or it destroys data. Keep in mind that improving availability usually leads to increased cost. When you consider how to make your environment more available, it's important to balance the cost of the improvement with the benefit to your users. Thanks for watching. See you in the next video. Welcome. As you have learned so far, you can use the AWS well-architected framework to understand potential risks in your architecture, identify areas that need improvement, and drive architectural decisions. In this video, you will learn about the AWS Trusted Advisor tool that you can use to design and review your architectures on AWS. AWS Trusted Advisor looks at your AWS Trusted Advisor looks at your entire AWS environment. Welcome. As you have learned so far, you can use the AWS well-architected framework to understand potential risks in your architecture, identify areas that need improvement, and drive architectural decisions. In this video, you will learn about the AWS Trusted Advisor tool that you can use to design and review your architectures on AWS. AWS Trusted Advisor looks at your entire AWS environment and gives you recommendations in 5 categories. First, we have cost optimization. AWS Trusted Advisor looks at your resource usage and makes recommendations that can help you optimize costs, such as eliminating unused and idle resources or making commitments to reserved capacity. Next up is performance. AWS Trusted Advisor can recommend you improve the performance of your service by checking your service limits, looking at your provisioned throughput, and monitoring for overutilized instances. Next, we have security. AWS Trusted Advisor recommendations can help you improve the security of your application by identifying gaps that you need to close and various AWS security features that you need to enable. AWS Trusted Advisor also examines your permissions. Additionally, we have fault tolerance. AWS Trusted Advisor recommendations can help you increase the availability and redundancy of your AWS application so that you can take advantage of automatic scaling, health checks, multi-AZ deployments, and backup capabilities. Finally, we have service limits. AWS Trusted Advisor checks for service usage that is more than 80% of the service limit. Values are based on a snapshot, so your current usage might differ. Limit and usage data can take up to 24 hours to reflect any changes. It's important to reiterate that AWS Trusted Advisor is a tool that you can use to review your AWS environment as soon as you start implementing your architectures. You don't need to wait until you have a fully built, production-ready environment. Thanks for watching. See you in the next video. It's now time to review the module and wrap up with a discussion of a practice certification exam question. In summary, in this module, you learned how to describe the AWS well-architected framework, including the 5 pillars, identify the design principles of the AWS well-architected framework, explain the importance of reliability and high availability, identify how AWS Trusted Advisor helps customers, and interpret AWS Trusted Advisor recommendations. Let's look at a sample question. A SysOps engineer working at a company wants to protect their data in transit and at rest. What services could they use to protect their data? The key words to recognize in this question are protect their data in transit and at rest. The correct answer is D, all of the above. Elastic Load Balancing, Amazon Elastic Block Store, and Amazon Simple Storage Service include encryption capabilities to protect data in transit and at rest. Thanks for watching.